I'm going to have a 15-minute talk, which will be kind of broad to sort of survey some of the results that we've had in these areas. And then after that, Hassan is going to go deeper for a half-hour talk, really focus more on one thing. So yeah, this is kind of like a thing I've been focusing a lot over the last 5-ish years, featuring a broad range of collaborators, including a few people in the room, including Hassan, my student Argyris, who many of you hung out with at the poster session. Maybe Matt is here yet to teach some sections. Maybe is he here? No, he's been in and out, I think. But yeah, Shai should be on this, but I forgot to add him, so sorry. But you can see him right here if you don't know what he looks like. Anyway, so yeah, let's talk about. We're going to start nice and simple with a problem that's probably familiar to many of you: non-private Gaussian estimation. Very, very familiar problem. We're given a data set and data points sampled from a Gaussian in d dimensions, and we want to estimate the distribution in total variations. Equivalently, this can be seen as estimating the parameters of the distribution, not quite in L2, but like in some appropriate transformation of it. If the covariance is the identity, then it is L2. But this is a very easy problem in the sense that we know how to do it pretty well at this point. You just can take the empirical mean, you can take the empirical covariance, and those will be pretty good estimates of mu and sigma, and you can just plug it in and give you a total variation estimate of the overall distribution. In particular, if you do this, then taking d samples will give you a good estimate for the empirical mean, which sort of matches the true mean, and taking d squared samples will give you a good enough estimate of the covariance that suffices for this total variation. And I want to highlight a few salient features of these very, very simple estimators that everyone's familiar with. One is that this works no matter where the data lies. It doesn't matter if like you have a zero mean Gaussian versus a Gaussian with a very large mean. You just take the empirical mean and it just works. You don't have to care where it is. Close your eyes, it's still fine. This may seem, okay, what's the big deal? But we'll return to that. Also, this is unbiased, in the sense that the expectation is equal to the true parameters. And these are very nice, convenient properties, which we had, immediately when you do the first thing off the top of your head. Any questions about this non-private setting in one slide? Pretty simple, hopefully familiar. Cool. But we're going to look at these. Yeah, question.
Is it okay to output a non-Gaussian estimate as long as it matches in total variation?
For today, we're just going to focus on estimating, a Gaussian. That's not really too big a detail here. You can choose parameter estimation or distribution estimation. They're both roughly the same today. Cool. But we're going to look at this under the constraint of differential privacy, which conveniently for Hassan, I'm presenting first, so I'll tell you my spiel. I'll show the formal definition, but it's really not that big a deal. You can focus on this picture I'm presenting, and I'll try to tell you like a game or like how you can think of DP in your head. So this is the kind of picture you should have. You can imagine there's some data set which is fed to an algorithm and produces an output. Now, alternatively, you can imagine a neighboring data set, which is just one data point added or something, is fed to an algorithm and produces an output. Now, an adversary takes a look at the output, and they're trying to figure out what was the input, was it x or x prime? And if they can't really do much better than randomly guessing, then we say the algorithm is differentially private. So it's kind of like hiding the contribution of one point in the data set. A little bit more precisely, the algorithm's distribution of outputs don't change much when you add or remove one data. If you're wondering about the adversary, you'll see when you walk back to your car after the end of the day. Anyway, so yeah, that's the rough idea of differential privacy. The idea that we're kind of masking the contribution of one individual to the data set. And just to, here's the formal definition. If you haven't seen it before, then this is probably gobbledygook. But it's like the distribution over outputs is similar for the algorithm run on x and the algorithm run on x prime, which differ in one input. I'll comment that this is a quantitative definition, which has two numbers, epsilon and delta. You can think of epsilon as being like 1 or something around that order, whereas delta is maybe closer to 1 over n, pretty small. But the idea is a quantitative definition, and as you take these parameters smaller, then then it becomes more private. But again, this precise definition isn't going to be too important today. Just think it's a rigorous notion of privacy. Cool. So what changes with privacy? Yeah. So one problem, when we try to just do the exact same thing, we're going to run into an issue immediately. And I'll show you a simple way to fix that. But we're going to see a lot of consequences that happen to this one fix. So suppose we have a data set which is like nice, kind of Gaussian-ish looking. I'm going to choose like a specific example just to illustrate something. We have a set of female heights, and we want to compute the average height. And so we picture this should follow a nice Gaussian distribution. And so let's just try to do the exact same thing that we did before, in the sense that non-privately, we just take the empirical mean for this data set. Now, this is problematic because this is not differentially private. And if you've ever seen anything about differential privacy, you'll know the simplest way to make any sort of statistic differentially private is add noise to it. In particular, we add noise to the statistic, which is proportional to the statistic sensitivity. So essentially, you take a look at the statistic that's not private, and you see how much can it change when you add or remove one data point. And you kind of add noise, which is comparably large to how much that statistic can move. So in other words, for a very sensitive statistic, you can add more noise, and for an insensitive statistic, you can add less noise. So if you think about that for a sec, you'll see instantly why we run into issues here. Any thoughts on what the sensitivity of mu hat is? Yeah, exactly. Uh-oh, I hope I don't have a meeting in the middle of this. No worries. Yeah, but that's the problem. The fact is, without any special care, okay, maybe I gave this for an applied class. You can see the sensitivity is a real max, or infinity for the theorists in the audience. I have both actually. But yeah, the point is the sensitivity of this is very, very large. And then consequently, you'll have that the amount of noise you have to add is infinite. So that's a problem. The first problem we run into when you try to privatize the empirical mean is the fact that the sensitivity is infinite, and you have to add infinite amounts of noise if you want to privatize it. This might seem like, okay, this is a silly solution, or a silly problem. There must be an easy solution. And of course there is, based on the fact that I told you, we're looking, animations here, but we're looking at, say, female heights, and we know that most females are between 120 and 200 centimeters in height. So you can essentially clip your data so that if there's anything outside these bounds, just either drop it, move it to the closest endpoint, something like that. The point is, if you look at this clipped empirical mean, then you're going to have something that has bounded sensitivity, and you can add noise to privatize it, a finite amount of noise. And one thing I want to highlight here is, which I'll still return to a little bit later, is a different estimator for those two cases I highlighted before. As opposed to before, you could just, again, close your eyes and just take the empirical mean. So in summary, we can privatize the empirical mean by instead looking at the clipped and noised empirical mean. Questions about that? Yeah. No, because here you're just going to average them all together after doing clipping, and then you're going to have some number, which is a true clip mean, and then you add noise afterwards. It's kind of done by a trusted curator, not individually. You can do it at the end. Cool. So this is like, the first differentially private statistic you could think of, and it works pretty well. But yeah, so let's see some implications of this. What comes up? I won't go into quantitatives about how these actually arise, but essentially we have to clip and bound the data, which you think is not such a big deal, but there's a few implications. One thing is, like I just told you, you have to first of all know where the data lies. So before, we knew that estimating the mean of, say, a Gaussian takes d over alpha squared samples. But my claim is that now in the private setting, if you want to privately estimate the mean, then you additionally need this piece of information. We need some sort of bound on where the mean lies. We can't just do it for arbitrarily large numbers. We need some a priori knowledge as a data analyst. And in fact, that shows up in the sample complexity. So you can't just use arbitrarily unbounded data. You have to have some prior knowledge, which is a bit challenging for an analyst. So we've kind of derived these bounds in a few works along with the other folks as well. We actually have some pretty good estimators which work on real data in the end. And I'll mention that, we can show all these terms are essentially tight. Some similar results for covariance estimation. I just focused on mean estimation for simplicity. This work is led by Argyris, who, he presented a poster, really cool work which he led. So the bad news here is that, again, you need the data analyst to have more information, and that's kind of annoying. There's two ways to alleviate this. One is by relaxing your privacy notion. This is kind of like for epsilon 0, or also concentrated DP, if you know what that is. But if you relax to epsilon delta DP, then actually 3 simultaneous groups thought this was a really interesting question and came up with answers on how to totally remove this requirement for the analyst in poll 22, including one by my group, including Argyris and my postdoc Vikram, but also one by Hassan and Christiao, and one by other folks. So, everyone converged to this problem. Another thing you can do is, what if you had just a small number of data points which were public? That is, you don't care about privacy, for just one data point, or maybe D data points. Then it turns out that we showed in a couple works that you can also similarly remove this knowledge on the part of the data analyst, which alleviates things significantly. That said, these are still a little bit more theoretical. It would be cool to see those in a more empirical and practical setting. So that's one challenge, the fact that the analyst needs to know where their data lies beforehand. Another challenge is the fact of bias, in the sense that before I told you that you can just take the empirical mean, which gives you a really good estimate of the true mean with few samples, and also it's unbiased. But we did this clipping of the data, right? You set these boundaries, and if anything goes outside, then you bring them in. That's problematic because that biases your statistic. You're sort of changing the distribution, and the empirical clip mean is not going to be the same as the empirical mean, or sorry, as the true mean in expectation. So the question is, can you do away with that? Maybe there's some other smarter way of treating your data that won't just do this clip and add noise, that can get rid of this biased issue. And the answer is unfortunately no, not even for Gaussians. You kind of can if you relax your privacy notion and use it. I say kind of the answer is yes in specific cases, but I'd say this is still kind of a no. And this is in a recent work with a lot of my group. And shoot, I forgot. I made this just before, but it includes Matt, who's now here in the back of the room, who actually was probably the main author of this. Yeah. Anyway, so this is really, I really like this work because this is, I think it's a new thing that people haven't really looked at, and I think understanding how bias comes up in these settings is something that we should look into more. So that's the second challenge. And the third thing I'll just mention very briefly is the fact that heavy-tailed data becomes harder. What do I mean by that? So what I've told you already now 4 times or something is the fact that estimating the mean takes this many samples. But you can also consider a setting with fewer assumptions on your data, where instead of knowing it to be sub-Gaussian or sub-Gaussian, let's just suppose that the variance is bounded. So only the second moment is bounded, maybe higher moments are unbounded. And in the non-private setting, this is still 1 over alpha squared samples. There's really no significant change in the rate here, the sample complexity. But with privacy, then it does change. I'll just show you, you can see the difference in this is the Gaussian case, and this is bounded variance case. You can see that there's an actual quantitative difference in how much data you require. And roughly speaking, this is because there's heavier tails, so you have to adjust where you clip your data and how much data gets cut off. It's kind of balancing the bias and the noise, which kind of ties back to what I told you in the previous slide. So, and this is inherent. You can show that all of this is tight. I forgot to even give a citation for this. Wow, but this was a work with Vikram Singhal and John Ullman back. Yeah, funny. So yeah, this is it just shows that another qualitative change in the amount of, in sort of the private setting as opposed to non-private setting. So anyway, I'm going to wrap up here, and I just wanted to hope it came across to you that private estimation comes with a lot of surprises. You need to know where your data lies. Bias is unavoidable. Heavy-tailed data is different And this is all just stemming from the fact that you had to clip your data. There's a lot more stuff which I didn't even mention today because I didn't have time. You could ask me about robustness, which has some really exciting connections, I think. But in the interest of being broader, I didn't go into it. And thank you.